Welcome to lecture 22. We are going to be talking about a new concept called virtual memory in this lecture. A quick announcement. So we extended the project 3 due date to this coming Tuesday. So we had some issues with power failures and it impacted the autograder submissions. And so we are providing this extension to help you all with those issues. I also want to point out that there is a tool available that could help you understand cache designs better. This is very similar to the tool that you may have used for simulating the pipeline. And so this tool is something that we built a couple of years ago. A student of mine helped me build this tool. And it's quite useful. It doesn't have all the functionalities that you would want, but it's pretty sufficient for understanding the basics of cache design. I would also encourage you to go and check out the cache organization in your computer. So if you're using Linux, you could use this command that I'm showing on the screen to figure out what the cache size is, and it can also give you some additional information about associativity and so on. So on my computer, which is Windows, I could find this out just by going to my task manager, and I found out that my processor has 3 levels of caches. So in this course, we talked about just one cache within a processor, but a modern processor has 3 cache levels. Why is that? Well, we know that small caches are faster, so we want small caches, but small caches don't have enough space. So you want to have both a small cache and a big cache. So if you guys remember the first lecture on memory systems, lecture 17, we talked about this analogy with a library, bookshelf, and a backpack, how you will need all of them to get access to the books very fast. Same idea again applied here for different levels of caches. So if I look at my cache, it looks like I have 256 kilobytes of L1 cache, but I also have 4 processor cores, which means that the 256 gets divvied up between those 4 processor cores. So each processor core, which is one pipeline, would have 64 kilobytes of data, but it's probably divided into instruction and data cache. So each cache is then going to be of size 32 kilobytes. And as I said, this is an L1 cache, and I have 4 processor cores all integrated within one chip. And each of these processor cores will have their own L1s. And I'm going to assume that my L2 is shared across the different processors, though I don't really know for sure. It's sometimes possible to design a private L2 where, just like in L1, you have divvied up L2 into 4 parts, and each processor core has access to that part. But I'm just going to assume that it is shared. And then my L3, in most processors, they're definitely shared. And then L2 is going to be, of course, much smaller. It's 1 megabytes, and L3 is 8 megabytes. I have not drawn the boxes to scale here. Okay, so that's my cache configuration. So go and find out what you have on your computing system. Okay, so before we get into virtual memory, it's worthwhile to understand a little bit of a motivation and a problem that we are trying to solve. And I would like to again go back to a slide from lecture 17 where we set up this whole problem of memory system design in the context of what an ISA program needs. So we talked about how an ARM64 assembly program would need access to 2 to the power 64 bytes of memory. That's a lot of memory. That's 18 billion bytes of memory. Cache is clearly not enough for that. And so far, we had assumed that main memory or DRAM is sufficient for it. That's how we were pretending all along. Hey, if you don't find data in the cache, go and find it in main memory. That's all we've been saying so far. Of course, that is not true. So if you look at this memory pyramid, main memory is typically a few gigabytes in size, maybe 100 gigabytes at most today. Now, that is nowhere close to 2 to the power 64 bytes of memory that we need. So clearly at some point you would run out of space, so you have to go to the next level of memory hierarchy, and that is hard disk. So far we have talked about the interface between cache and main memory, how processor manages the data movement, and today we're going to talk about the interface between main memory and hard disk. And it turns out that it's not the processor that manages this transaction, but it is the operating system that manages this transaction. This one was processor, and there is good reason for that, and we will understand that later on, but this is an important distinction to understand. So it's also useful to visualize the different components that goes together in your computing system. So far in 370, we were primarily concerned about the processor design. We started off by talking about an ISA, which specified the functionality that a processor has to implement. And we then talked about a pipeline data path that implements the instructions. And then we said we want caches that holds the data and instructions so that the pipeline can quickly read and write to different addresses. And that's what you see here, the caches. And we simplistically assumed that your main memory, which is off chip, takes a long time to get there relative to your caches, is large enough to hold all of your program's data. Obviously that is not true, and so we need to worry about spilling the data to your next level, which is another device. Today in modern desktops and mobile phones you have SSD flash, which is much faster, but we used to have hard disks, and which is still widely used in many systems and data centers for backup storage and so on, which is very high density and cheap. In 370, whenever we talk about disk, we are referring to one of these non-volatile devices that is meant for storing the data that spills over from main memory. I'm not going to make a distinction between these two, though they are significantly different in terms of the technology, and as well as the latency of flash is much better than hard disk. But I'm just going to ignore all that and just assume that we have backup storage to store data that spills over from main memory. Okay, so let's now talk about virtual memory. Like I said, virtual memory is actually an operating system functionality. So in 370, now we are learning about an OS functionality, which enables multiple concurrent running programs to share the physical memory and the swap disk. On my computer now, I'm running PowerPoint, but in the background, I'm also running web browsers and video editing software and so on. So there are several processes that are running simultaneously, and they all need to share whatever hardware resources that I have on my computer. And so virtual memory is an OS functionality that allows these multiple programs to share data, share the hardware resources without stamping on each other. Okay, so it's not only the fact that a program's data is managed by the operating system, but it's also going to manage multiple programs that are running on the computer and their data at the same time. So though virtual memory is largely an operating system functionality, its performance would be very poor if we didn't have sufficient hardware support. So next lecture, we're going to talk about a special cache called TLB that is going to make whatever functionality that I'm going to talk about today much faster. So there are two roles that a virtual memory plays. One is capacity, which is somewhat intuitive and you already know about it. So we said a program needs space to store its data. Cache is not enough. And then we went to main memory. Main memory also may not be enough. So then you need to go to the disk. Soon we'll realize that even disk may not be enough, but we'll come back to that point later. So the point is, we need virtual memory to manage a program's data and store it physically on your main memory and then your disk. That's problem number one. Virtual memory also solves a second problem, which is security. Like I said, a computer runs multiple programs at the same time. So you need to make sure that unrelated programs don't get to see each other's data. This property is called isolation. And it's often also useful to have permissions associated with data. So for example, I may not want to modify my instructions, or if my heap address has not yet been allocated, then I shouldn't let my program go and read or write to it because I haven't really allocated it. I mean, the programmer hasn't really allocated it. And so when your program tries to access an unallocated heap, it's better to raise an exception instead of continuing with the program execution incorrectly, grabbing some random data. So that's why you would see segmentation fault, and we'll see how virtual memory can help implement those functionalities as well. So first, let's focus on how to provision sufficient capacity for your programs. So first, we want to expand our available capacity from main memory into the disk space. When I say disk, I'm also referring to the flash. Now, a flash or a hard disk, they have space to store files like your images and videos and PDFs, or your even software that you have downloaded. All that is stored in this disk, and they all take advantage of its non-volatility feature, because if you turn off your power, you don't want to lose your images, so they stay where they are. And that is different from a special space that is allocated within a disk called the swap partition. The swap partition has only one role. Its role is to store the data that spills over from main memory and serve as a backup store. And if you want to know how much of your hard disk space is allocated for this purpose, if you're using Linux, you can type this command top and you will get to know how much of space has been partitioned for it. As a user, you can decrease or increase the space depending on how many programs you would like to run at any given time, or how much you really need your hard disk space for storing your images and videos and whatnot, right? So it's up to you to program it. Now here is a very important slide which really explains this construction of a virtual memory. So it's very important to understand this picture. So let's start by understanding the two boxes on the left and the right, the virtual memory and the DRAM. Ignore everything else. Ignore the page table that's there in the middle. For the moment, also ignore the disk. So let's start with virtual memory. So what is really virtual memory? It's really the memory that you have been using all along. Like when you wrote your C program, when you go and access an address, the address that you accessed is actually a virtual address. And if you wrote a LC2K program and the address that you generated through your load and store instructions, those addresses are also virtual addresses. So if you have a 64-bit ISA, you have total of 2 to the power 64 number of addresses or memory locations. Now, all of this memory that you see here on the left hand side, it's virtual memory because it doesn't really exist in reality. It doesn't it's not all of it is stored physically somewhere in your computing system. It's just virtual. It's there in a programmer's mind. Okay. Now that doesn't seem that reassuring, the fact that virtual memory is not stored in your computer and still we are able to run the programs. So what's really going on here? Well, we do have physical memory, which is what I have shown on the right hand side, which is composed of your DRAM, main memory, which is, as the picture illustrates, is much smaller than the virtual memory. So at any given time, it can only store a subset of the memory locations in your virtual memory. Now you can expand the space a little bit by grabbing some space from your disk. We call this as a swap partition, right? And that increases the number of virtual memory locations that can be physically stored. Okay. Now we're going to call the addresses that refer to a physical location on either the DRAM or the disk as a physical address, which is different from the virtual address that we talked about earlier. Okay, so now we have virtual addresses, which is defined by the ISA, and we have physical addresses that refer to physical locations on your computing system. So now we need to find a map between these two, and that's the job of the operating system. So now when you start a program, that program starts off by the operating system creates what's called as a page table for that program. And that page table starts off by allocating space in the physical memory for your program. So when you start off, that space would be for instructions, your data segment, and you probably don't have anything for a heap, but that's going to get allocated as you execute your program and call a malloc. Then you will start allocating on heap, and then as you invoke functions, then you will start allocating stack frames. So the text, data segment, heap, and stack that we talked about as ABI, going back to the initial few lectures of 370, that exists only in the virtual address space. Now as you execute your program, you ask your operating system, hey, I need more space, I need more memory, I need more address locations to be physically stored. And operating system kicks in and it allocates memory on demand. So it doesn't give you all the space that your virtual memory needs right away. It doesn't give, when you start your program, the operating system doesn't go and say, hey, I'm going to allocate you 2 to the power of 64 byte worth of memory locations. No, it doesn't do that. Instead, it gives you space only when you ask for it. So it starts off by giving you space for your text and data segment, and then gradually it gives you space for your stack and heap. And so it creates this data structure called page table, and I'll tell you why it's called page table later on, but assume that it's just a table that maps for every virtual address a corresponding address in physical memory where that address is stored in. So for example, the virtual address 0 maps to the physical address 5000. So you follow the arrows here and you will see that the black box representing the data that is stored in the address 0 of the virtual memory is actually physically stored in address 5000 of your physical memory. And similarly, the data in address 1000, the darker gray, is stored at address 0 of the physical memory. And then the lighter gray is corresponding to the virtual address F30 is stored at the physical address 9000, and that's what you see here. Sometimes you may not have enough space in your physical memory of DRAM, and so you may need to store, meaning the operating system needs to store that data in a physical location that corresponds to the disk. So D1000 refers to an address on the disk, the swap partition that we talked about. Now, I want you to ask yourself a question. Can we store all the data in virtual memory? So let's say I said that the operating system would allocate physical space on demand. So let's say you write a program in ARM64 and you keep asking for more and more data, meaning you want to allocate more and more space. If you keep asking for more and more space, would it be possible to allocate a maximum space that you may ever want to ask, which is 2 to the power 64, somewhere in your system? And the answer is no. It is a scam in a way that your operating system is running. On one hand, it is telling the programmers that, hey, you have the guarantees of the ISA. The ISA tells you to use any memory location that you want between 0 to 2 to the power 24. And I guarantee you that whenever you need physical memory space, I'll give it to you. But if you do want to provision that much of space, it would be super expensive. Now let's think about how expensive that would be. So if you have to store 2 to the power 64 bytes of storage, forget about DRAM. Even on a hard disk, if you want to store that much of data, it would cost close to $1 billion. So you obviously don't want to pay $1 billion computer for just running one x86 64-bit program, right? So clearly that is not a feasible idea. So what do we really do? What does the operating system really can do? Well, it just fakes it. It doesn't have space to store all of the data that you may ever want to ask from your program, and so it just provides an illusion that you have it. So now you may ask, okay, what happens when I do ask for the space that I was promised? Well, then your computer will crash. So you may have seen this screen. This is not an uncommon sight. You have run out of memory or system resources. Now this error message should never happen if your computing system had enough space for all the data in virtual memory space. But the reality is, like I said, that's impossible, especially if your ISA is 64 bits. So that's why you often see that your software comes recommended with some physical memory space. And the expectation is that even though the programmers have the luxury of using 2 to the power 64, they are disciplined enough to not use more than what they need, and that typically happens to be less than what physical memory space that we have on our modern systems. And you don't want to write software that exceeds that common space that is available in modern systems. If you do that, then nobody will buy your software, because your software will just keep crashing and throwing up this message, and obviously you won't be happy about that. So the takeaway message here is that even though the ISA guarantees so much space, modern systems don't really have that space, but it's still good to have this guarantee as part of the ISA, because it makes it future proof, meaning in the future, as your computing systems become more powerful and have more space, then you can start writing more sophisticated programs that consume more and more space. But today, you as a programmer has to be disciplined enough to not use all this space that you are allowed to under your 64-bit ISA. So to recap, virtual memory is an operating system functionality that allocates physical memory space on demand to a given program. And it maintains this data structure called the page table, which maps every virtual address to an allocated physical address. It's possible that many of these addresses have not yet been allocated, and if they have not been allocated, the corresponding entries for them in the page table would be set to invalid. Okay, so now let's go through the implementation of this page table and understand the mechanics of the address translation. By address translation, what I mean is the process of translating a given virtual address that would be generated by a load or a store instruction. When you execute it in the pipeline, it will generate one of these virtual addresses, and we want to understand how to translate this virtual address to its corresponding physical address by looking up into the page table. And we'll also try to understand how could we reduce the overhead of the size of this page table. And then we will later on in the next lecture, we will talk about how to perform this translation much more faster with the help of the hardware support in the form of TLBs. Okay, so now let's just talk about what does the operating system do to translate a virtual address to a corresponding physical address. So a virtual address is what you get from a load or a store instruction, and we want to convert that into a physical address. So to understand how this conversion happens, first we need to think about what should be the translation table that operating system needs to maintain. So we talked about this table called the page table, and so far I've been saying that for every virtual address there is an entry in the page table that tells you where the physical address is. Now if you think about it, the overhead of such a translation table will be huge, because we have a huge number of addresses. We don't even have space to store data in all those locations. It would be unacceptable to have the page table to be big enough to store entry for each one of these valid 2 to the power of 64 memory locations. That would not be a good idea. And this problem must remind you of the same problem that we talked about when we designed caches. When we said, oh, there are too many tags in the cache and the tag space overhead in the cache is too much. So can you recollect what idea we used to solve that problem? The idea was to increase the granularity of data that we maintain per tag, right? So in this case, we don't have tags, and there's a good reason for that, because we have this special table that does the translation. So we don't have tags, but we do have to worry about the size of this table. And so we want to reduce the number of entries. So you can reduce the number of entries by employing the same trick. Instead of maintaining an entry per address location, I'm going to maintain it for one block of address locations. And that block, I'm going to call it as a page. And pages are very similar to how we were thinking about cache blocks before. So instead of calling it as a main memory block or a operating system block, we just wanted to give a new name. So we're going to call them as a page. The page size typically is about 4 kilobytes or so. And today in modern systems, there is an argument for having much larger pages, but around 4K is a reasonable size to assume for now. And we are also going to say that the size of the virtual page is same as the size of the physical page, which obviously must be true, because anytime when I want to ask operating system to give me space, I want to grab space at the granularity of a page, a virtual page. So I will go and ask, the program will ask, okay, allocate space for this address, please. And the operating system will say, okay, which virtual page is it? Okay, you don't have space for that yet, so let me allocate a physical page for you. So all maintenance is done at the page granularity, much like how all maintenance was done at the cache block granularity in the case of caches. So just like block offset, we have page offset, which are a set of lower order bits that index into a given page. And the remaining, we used to call them as tag in the case of caches, but now we're just going to call them as virtual page number, or sometimes we just abbreviate it into VPN. A virtual page number is a number that corresponds to which page in the virtual memory are you talking about. And so address translation would have to look up this page table for a given process and say, okay, look up the translation for my VPN, and the page table will have an entry that says, okay, the corresponding physical page number is this, and then out comes your physical page number. So, and then you do the translation, and the page offset would remain exactly the same. That doesn't change at all, because address translation has nothing to do with it. The translation happens at the page number granularity. That's what you're translating. The page offset does not need to get translated because it's a constant across the virtual address and the physical address. So that's one thing to remember and understand. Page offset is exactly the same for the virtual address and the physical address. What changes is the virtual page number, which then gets translated into a physical page number. So now if I increase my granularity to 4 kilobytes, the number of entries will decrease by a factor of 2 to the power 12. So before I needed 2 to the power 64 number of entries in my table. Now I would need only 2 to the power 64 divided by 12. So I would need only 2 to the power 52. So I have 2 to the power 52 virtual pages, and for each virtual page, so each virtual page has an entry in the page table, and the page table entry tells you the physical page number that corresponds to the virtual page number, and using that you can do the translation. Now you may have observed now that 2 to the power 52 is not a small number either. To allocate a page table of that size for every program would be too expensive. So in the next lecture, we're going to talk about another idea called the multi-level page table that would solve that problem, and we'll see how we can dramatically reduce the size of the page table using that idea. So the data structure that the operating system uses to perform the virtual to physical address translation is called the page table. And each process has its own page table, obviously, right? Because there is an entry for every virtual page of a process in the page table. So each page table belongs to just one process. That's really important. And the page tables themselves is simply a data structure. Think of them as an array that you have in your program. So they need to be stored somewhere too. So they tend to be stored also in memory. So it's OS that manages it, but OS stores that page table in memory. So even OS needs some data to function. So page table is the data that operating system keeps around to manage the processes that it is managing, right? So operating system stores this page table in memory as well. And so the question now is, when the operating system needs to do an address translation for a process, how does it know where that process's page table is? So we said the virtual address is translated to the physical address by using this page table, but first you need to go and find the page table, right? And so the address to the page table of a process is maintained by the operating system in a special register called the page table register. Now, if you're running a program on a processor, within the processor, you have a special register called the page table register, and that register is initialized with the first address in the page table. So the page table register points to the first address. So whenever your load or a store generates a virtual address and you want to translate it, the way you would do it is, of course, you would ignore the page offset because that doesn't play a role in this translation at all. You grab the virtual page number, and you also know the page table register, the base address of the page table, and then so you go and figure out where your page table is in memory. So then you get this page table that I have indicated using this yellow box. And then you take the virtual page number, and so far we have been assuming that for every virtual page number there is an entry in the table, and so this would be a simple index into this big array. So it will be as if like array of I, right? It will be like page table of VPN. Then you will get to this entry, and then you can look up that entry, and then you get your physical page number. You also have this valid bit. And recollect what I said about heap and stack. They are not immediately allocated when you start your program. Only the instructions and data segment is allocated. It's only when you start executing your program, the program would call malloc, and then you would allocate data on demand on the heap. And when you invoke functions, you allocate data on demand on the stack. When those things happen, then these entries will start getting populated, and more physical space will be allocated for your program. And hopefully you don't run out of all the physical space that is available on your system, but if you do, then your program will crash. Alright, so now you look up the page table, and then that gives you the physical page number, and if you concatenate that with your page offset, what you get is your this is physical address. Okay, so here is a more concrete example where we have these values for virtual page number and the page offset, and then this is value 4, so this is 0, 1, 2, 3, 4, and then you go and look up your physical page number, which is this, and then you concatenate with the page offset. And so this physical address would refer to a unique location either on your DRAM or on your swap partition on the disk. Okay, so what are page faults? I said that you take your virtual page number and you look it up, right? It's possible that you have, as an operating system, allocated space for it, but that space now exists on the hard disk. And this usually raises an exception because accessing data from main memory is fairly fast. It's much slower than accessing the cache. It's hundreds of cycles, but it's just hundreds of cycles. But if your data resides on the hard disk, it's going to take 100,000 cycles, some ridiculously long time. And so you cannot stall your program on the CPU for that long, because then you will be wasting your CPU just idling around waiting for the data to come back from the hard disk. So typically what operating systems do in that scenario is they want to be informed that the data is not there in the main memory, and then you got to go to the disk. So when you do the address translation, you find out that the address is actually the disk address and not the main memory. And this raises an exception to the operating system. This exception is called the page fault exception. And this exception handler would be a software routine that runs to go and figure out the position on the swap partition for this disk address and then grab data from there. In order to do that, typically the page fault handler would stop the process that you're running, because you don't want to be idling around. And so and then you'll pick a page in the main memory to replace, because now you're going to bring back that data that you just accessed, because you want to exploit temporal locality. Remember that the data that you're accessing now is more likely to be accessed in the near future than the one that you least recently used. So most likely you would use an LRU type of a policy to replace the data from main memory. And then whatever victim that you choose need to be moved from the main memory to the disk, and then you will get the read the data from the disk, bring it to the the main memory, and then you update the page table with the new physical addresses for the two pages that you swapped, and then you reschedule the process. So you would context switch in the middle of these things. So when you say write back the data, so the operating system will hand over the control to DMA and schedule some other process to use the CPU in the meantime, so that hundreds of thousands of cycles that goes into writing or reading data from the hard disk does not hold up the CPU from doing useful work. And that's how it's done this way. But the main point to understand for page faults is that a page fault is like a cache miss for caches. In this case, you have missed the data in the main memory, and so you have to do that eviction and replacement with new data. Okay, so here is another representation of those steps that I just described. So the load that is executing in your processor's pipeline wants to access the virtual address M, and you translate that address by looking up into the operating system's page table, which then figures out that, well, this page is not there in the main memory as indicated by a bit in the page table entry. And if that's the case, then the operating system raises an exception, and so the operating system routine called the page fault handler kicks into action. It's essentially a software routine which is responsible for identifying a victim in the physical memory and reading data from the disk and bringing into that freed up space, and also writing the data that from the physical memory to the disk space. It does the swap, and then it makes the necessary changes to the page table and then restarts the whole program. So to conclude, virtual memory is operating system functionality. When a process is launched, when you start a program, the operating system allocates a page table for that process. And it is the operating system, in particular, it's a page fault handler, that is responsible for identifying the victims and finding space for a page in the page table in the main memory and swapping it from the disk. So it's all the operating system that is responsible for deciding what data should be replaced and when they need to be brought into the main memory. Now, the operating system is also responsible for doing this address translation, but keep in mind that this address translation needs to happen for every load and store. So it's a very performance sensitive operation. And therefore, you need some help from the hardware to make this go faster. So that's going to be the topic of discussion later on in this course. And we're going to talk about how to do this address translation very fast. So VM is a perfect example for a hardware-software collaboration. We often call that as a hardware-software co-design, where the OS is responsible for some functionality. If you wanted, you could implement everything in software, but then address translation will be so slow that your virtual memory feature will be very expensive. So modern processors provide some simple hardware support to make this process go really fast. I would also like to draw similarities and differences between the cache design versus how we are thinking about the main memory design. So the first thing that should be clear by now is the caches were managed by the processor. When you wanted to access an address and if it is not there in the cache, it was a processor that decided which cache block to evict, and it's a processor that kept track of the LRU bits and everything. So that's entirely a processor's function. The main memory, on the other hand, is maintained by the operating system. And it's the operating system that is in charge of replacing data and bringing data into the main memory. The terminology wise, the difference is cache block is what we had for caches, and for main memory, it's the same block is referred to as a page. Now, cache blocks tend to be around 64 bytes to about 128 bytes or so. A page ranges from 4 kilobytes, and some super pages can go up to even 64, 128 kilobytes today. Okay, so it's and 2 orders of magnitude larger than a cache block. And when you have a miss, it's called a page fault in the case of virtual memory, and unlike in the case of a cache where you just go to the main memory looking for the data, in the case of a page fault, you will have to go to the disk to find the data. That is, if you have already allocated it. In some cases you may not have allocated it. In that case, you don't have to go to the disk, you just initialize a page and then you can start using it. Now, here is an interesting relationship between how we thought about caches and how we are treating main memory. So most processor caches are set associative. It's very rare to use a fully associative cache. Most of them are set associative. In fact, an L1 cache is more likely to be direct mapped, at most two-way, because they're so latency sensitive. But if you had observed the main memory, the way it's being treated, we are thinking about it as a fully associative cache. Why is that? Well, we have this virtual memory, the virtual address space, right? And we had this data structure called the page table in the middle. And then we had this physical memory space. So there's a virtual memory, and this is, let's say, the physical memory, and this is your page table in the middle. Now, because we had this page table, I could just look up this page table and find out, okay, where is my data? And I can go and grab the data from there. So there's no tag comparison that is necessary, like it was the case in the case of caches, where we didn't have this page table. And so because we didn't have this page table, we had to explicitly store the address as part of the cache. And whenever you wanted to check whether you have the address or not, you have to go and do a tag comparison with all the cache blocks that is there in the cache, if it's a fully associative cache. And that was too expensive to do all those comparisons. So instead of doing that fully associative search by doing all those comparisons, we can avoid them by simply having this page table and looking them up and figuring out where the data is. Now, if this page table is such a good idea, why did we not use it for cache design? Think about that. Well, the main reason is a problem that we have not yet solved is the page table is not free. It consumes a lot of space, and we're going to play a lot of tricks to try and reduce that space. But creating a cache table for every cache would be super expensive, because you need an entry for every virtual cache block, right? That corresponds to a physical cache block in the cache. And creating such a cache table would be super expensive and not worth it. Though some researchers have tried to approximate that, and they have thought about finding more efficient ways to implement it, but that idea hasn't really taken off. Now, because of the fact that I have this page table, it allows me the freedom to select a victim from anywhere in the physical memory, and that's why my main memory is being treated as a fully associative structure. Now, you'll also notice that I said it's an exclusive cache. What that means is a given data either resides in the main memory or on the disk. So if I have a page in the physical memory, this is, let's say, the DRAM. So if I have a physical page allocated in DRAM, I would not have a page allocated on the disk for it. I don't have any duplicates between physical main memory and the disk. And that's why it's exclusive. A given physical page is either in the DRAM or on the disk, and not in both places. But if you think about a cache, a given cache block is always has a corresponding copy in the main memory. Now, there is a reason why this is also an important thing, because the reason why this is not such a big problem for caches is, even though it's duplicating the data, cache is a much tinier fraction of the main memory, right? So cache, if you think about it, is only at most a few megabytes in size, the loss level cache. Whereas your main memory could be hundreds of gigabytes, right? So that's like 1,000 times, 100 times bigger than caches. So the fact that you're duplicating the contents of cache in main memory is not really that wasteful. And it makes the design so much more cleaner and easier, because otherwise you have to bring a little bit of a cache block here and you free up the space for it in the main memory, and then the question is, what do you really do with that space? You have to ask the operating system to allocate that space for someone else. It's so messy. So it's not worth optimizing, and it's too difficult to optimize. So that's why modern systems duplicate the contents of cache and main memory. They don't bother optimizing it. However, in the case of physical memory, the DRAM versus disk, anytime when you have a page fault, it's the OS that comes in and says, okay, I need to swap the pages. And so there's no reason to have a copy of everything that is there on the DRAM on the disk. You can just move it out whenever you need to. So, and that reduces, if you have to keep duplicate of main memory on the disk, and given that main memory these days are about 100 gigabytes, you would be wasting about 100 gigabytes of data on the disk, and that's kind of wasteful. So people like modern systems, they don't really do that. So that's why one difference is that the way that we are thinking about main memory is to disk is exclusive. A given page resides in only one but not both. Whereas in the case of caches and main memory, caches was inclusive, meaning whatever data that caches had, main memory also had the data. Consider the following virtual memory problem. This is very similar to the type of cache problems that we solved, except that in this case we are going to simulate how the virtual memory would be maintained by the operating system. So we are given the size of virtual memory and the physical memory, the size of the page, and the type of replacement policy that the operating system uses for main memory. We are also given the initial state of the page table, and then we are asked to figure out the other aspects of the virtual memory. After we figure that out, we are also going to simulate the virtual memory for a sequence of addresses. So first, let's take this information and construct how the virtual memory structures look like. So we are given that the ISA is a 20-bit ISA. So what that means is your virtual memory size is 2 to the power of 20 bytes. Now that virtual memory is divided into pages. Each page is of size 4 kilobytes. So if each page is of size 4 kilobytes, and if your total memory size is 2 to the power of 20, to compute the number of pages in the virtual memory, you have to divide the total virtual memory size by the page size, and then you will get the number of pages in your virtual memory. So I have 256 pages in my virtual memory. So the address for virtual memory goes from 0 to 2 to the power 20 minus 1, and the number of pages I have goes from 0, 1, 2, 3, and all the way up to 256. So I'm not going to consider every memory location. I'm just going to think about it in terms of the number of pages. So if you recollect, we're going to call these as virtual pages. So these are virtual page numbers. Okay, so now let's look at the fields in my address. So my page size is again 4 kilobytes, which means that the page offset size, just like how we computed the cache block offset, it would be log to the base 2 of 4 kilobytes, and that would be 12 bits. So page offset size is going to be 12 bits, 0 to 11. And then the remaining part of my virtual address is going to be the virtual page number. So that would be from bits 12 to 20, which is in total 8 bits. So the virtual page number is of size 8 bits. The page offset is of size 12 bits. So together you get 20 bits. Now if you'll notice, 2 to the power of 8 is 256. So that's how many pages we said we have in the virtual memory. So everything works out fine. Now let's take a look at the physical memory size. So in this problem, we are not going to worry about disk. We are only focused on the main memory. Main memory, composed of DRAM, is much smaller, obviously, compared to the virtual memory. And in this problem, we are told that the physical memory size is 16 kilobytes. So if you want to compute the number of physical pages, you would do the same math we did for the virtual memory pages, except that in this case, you will take the physical memory size and then divide it by the page size, which is 2 to the power of 12, and so you get 4 pages as your answer. So my DRAM has space for 4 pages, so my physical page number would be 0, 1, 2, and 3. So this is my PPN. Okay, so that's my physical memory. So if you recollect, virtual memory is just defined by the instruction set architecture, so that is a programmer's view. It doesn't exist physically in your system. What physically exists in your system is the physical memory composed of DRAM. To find out where a given virtual page is physically stored, the operating system is going to maintain a data structure called the page table. And page table is nothing but an array that is as large as the number of virtual pages, because for every virtual page we need to know where it is stored or if it is invalid. So we need one entry for every virtual page. So the number of entries in the page table would be same as the number of virtual pages. So we have 256 entries, one for each virtual page. So we have 256 entries, one for virtual page. Each entry consists of the physical page number that corresponds to that virtual page number. So there is a one-to-one correspondence between the virtual pages and the entry in the corresponding page table. And the page table may say, oh yeah, this is valid, and the physical page number is this. So the size of each page table entry would be the valid bit, which is 1 bit, and the physical page number, which we know is only 2 bits in size. So it's much smaller than what your virtual memory page is, which is, we know, is 4 kilobytes. So for each 4 kilobyte virtual memory page, we have one entry in the page table, and that entry is of size 2 bits for the physical page number and a few metadata like valid bits. Okay, so in the problem that we are working on, we are also given the initial state of my page table. Let's go and try to find out what that initial state is, and so we will try to represent that here. So first, the page table has to be stored in main memory. So we are told that it is stored in the physical page number 0. So this is the data structure that the operating system has, and the operating system has decided to store the page table itself in the physical memory. So the page table that is stored in the physical page number 0 is pinned. What that means is it is not going to get replaced ever. So when you run out of space in the physical memory, which you will eventually, the data pages will be chosen as victims, but the operating system does not want to replace the page table. And there is a good reason for that, because page table is most likely has good locality going forward, because you're going to need it to do the address translation. So it's the good idea to always keep it in your physical memory. Okay, so now let's take a look at what other virtual pages have been allocated and where they are stored. We are also given that virtual page 0 is stored in physical page 1. So let's take a look at how that would look. So virtual page 0, which is this entire 4 kilobytes worth of data, is stored in physical page 1. And the address translation for this is of course going to be maintained in the page table. So like I said before, for every virtual page there exists a corresponding entry in the page table, and that entry is going to tell you that the physical page number for virtual page number 0 is 1. And that's how the operating system can locate the data for this virtual addresses from 0 to 4 kilobytes. We are also given that virtual page 1 is stored in physical page 2. So just like what we did for the previous example, we are going to say that, let me change the color here. So virtual page number 1 is stored in physical page 2. And the translation for this would be stored in your page table. All the other virtual pages are invalid. So that means that the all of these pages have not yet been accessed by the program, and there would be an invalid bit that would be set to true for all of these pages. And this uses this principle of on-demand page allocation. So the operating system does not allocate all the physical pages that you need for the program right away. It allocates it on demand. So when you start off your program, the operating system would allocate space for the page table of that program and maybe a couple of physical pages to store the instructions and the data segment. The heap and the stack have not yet been created, so they would remain unallocated. So this example illustrates that initial state. So now that we have constructed the structure of the virtual memory, now we are going to simulate the virtual memory if assuming that a program is going to execute the sequence of virtual addressees. So again, when you execute a load or a store in the pipeline, the address the load and store would create, this is by adding the register offset RA with offset in your load instruction or store instruction, the address that the pipeline generates is the virtual address. And now we just figured out that the page offset is of size 12 bits. So this being a hexadecimal representation, 12 bits represented using 3 hexadecimal digits. So this part of all the virtual addressees would be the page offset. And page offset is not important for address translation. The page table converts the virtual page number into the physical page number. So let's just determine the virtual page number, which is everything except the page offset. So that would be 0, 0, and so on. Okay, now the problem asks you to determine whether access to this particular address is going to be a page fault or not. Page fault is nothing but like a cache miss in the case of a cache. So when a memory access does not find data in main memory, it would be considered as a page fault. So now let's think about whether an access to this virtual page 0 would be a page fault or not. To answer that question, we have to look into our page table, and we see that the virtual page 0 is stored in physical page number 1. So the good news is that the virtual page is allocated in main memory, and therefore it is not a page fault. So this is not a page fault, meaning it is a hit in the main memory. And the physical address would be the physical page number, which is 1. So this would be 0, 1. And then the physical address would be a concatenation of the physical page number with the page offset. And the page offset does not change, so we just have to rewrite that over here. Now let's take a look at the next virtual address, 01 FOC, which the virtual page number we have already figured out to be 1. We'll check the page table and we'll see that the virtual page 0 is stored in physical page 2. So it is actually a hit in the virtual memory, hit in the main memory, and so this is not a page fault again, and we said it is stored in physical page number 2, and again the offset does not change. Now for the next virtual page, which is 20, somewhere, let's say it exists over here, and we assume that all of these pages are invalid, meaning they don't exist in the physical page, and so we have to allocate a physical page for it. So this would be a page fault. The page fault handler would be invoked, and the operating system has to allocate a page for it. And so let's say I'm going to grab the remaining physical page, and I'm going to store this new data let's say my new data for 20 is over here, and I'm going to do the same exercise I did before. Let me change the color to blue. So this data over here is going to be now stored over here, and the translation for that is going to be stored in the page table. So this would say the entry 3 now has the entry 3 has the data. So this I'm going to allocate to the physical page 3. So therefore the physical page address is 3, and the offset does not change. It's same as what you have in the virtual address. Okay, so for the next axis 0, we know that page 0, the virtual memory page 0 is stored in physical page address 1. So this would also not be a page fault, and the offset is different for it. So you just have to copy that over here. The next one is also virtual page 0, which we know it's already allocated. The physical page number for it is 1. And then you copy this page offset here. And then you have different virtual page, which we have not yet accessed before. So therefore this would be a page fault. And now you need to find space for this new page. So now we have to allocate a physical page for this new virtual page 30. Let's go back to our representation here. So 30 is currently invalid, meaning it does not have a physical space for it. Now we need to figure out which physical page to free up, and we would use LRU policy for it. So of these 3 colors that you see, which one is least recently used? Well, if you go back to the previous picture, so we just recently used 0, and then before that we used 20, and so 01 is the least recently used. So you should be keeping track of the LRU rank to figure this out. And so now I know that 01 is the least recently used, so I'm going to free up this page. I'm going to now allocate this page to the address 30. And so let's say that I have a new color for this. Let me give purple color. So I have this new page, and that new page needs to be now stored in address 2. So I no longer have the green anymore, so I need to erase that off, and instead I have to replace that with the new color. This is the new page. And so the new mapping has now changed from invalid to now you have allocated a page for it, which is 2. And the previous page is now going to be invalid, or we could say that it would now be stored on the disk. So now this is not part of this given problem, but in practice, the operating system will move that green page to the disk. We don't need to know this for this problem, but it's helpful to understand how this whole thing works. So the green page would actually be evicted and found a space in the disk. Okay. And if later on, if the program were to access this page, it would still incur a page fault because you don't have a hit in the main memory, and the page fault handler would not create a brand new page for it, but rather move the old data that is backed up on the disk and copy that to the main memory. Okay, so now we have allocated a page for the new virtual address 30 that we saw. We evicted the data from the physical page number 2, and you allocated it to this new virtual page 30. So the physical page number is 2, and again the offset, you just have to copy it from the given virtual address. The page offsets are a constant across the virtual address and the physical address. Okay, now let's look at the next one. Unfortunately, we just evicted this page, and it so happens that the program accesses an address from the evicted page. we made our replacement decision based on the least recently used heuristic, and as we know what is true about heuristic, it can always go wrong, and that's what happens here. So now we have to evict least recently used page to bring in this new, not new, but like the old page that got evicted. And so the least recently used would be the address 20. So we just accessed 30. Before that we accessed 0. So therefore 20 is the least recently used, which is stored in physical page 3. So I would allocate physical page 3 for it, and this is also page fault. So 03 0 0 0. Sorry, this one would be the page offset is FFF. And now we are going to access the same virtual page 0, which we know has been allocated at 0 1. So this is not a page fault. So this is 0 1 2 0 0. Right? So that, in addition to providing sufficient capacity for a program, virtual memory also has some useful security functionalities. So there are two functionalities that we will talk about. One is isolation and the other is permissions. Let's talk about isolation first. So when you look at the task manager, if you're using a Windows computer, you will see the number of programs that are simultaneously running on your system. In my system, I have about 248 different processes, and they are running more than 3,000 threads. And so these correspond to a variety of programs. Like Chrome itself may create tens of processes. PowerPoint will have tens of processes for a variety of different tasks and so on. So the point here is that you're not running one program at any given time. You're running hundreds of different processes at any given time. And they all share the same physical memory space and the disk space. And we want to make sure that these unrelated programs do not get to access each other's data, because if they do, then it can have significant security vulnerabilities. So the virtual memory allows us to isolate the data that is accessed by one program like Chrome from the data that is accessed by a different program like Windows or a Bash shell, even though they all store the data on the same physical device. So how is this possible? Well, the trick is each of these different processes have their own virtual address space as defined by your ISA. So in a 64-bit ISA, like we've been talking about, the address space ranges from 0 to 2 to the power 64. And that's true about every individual programs. True for Chrome, true for Word, true for Bash, or any other program. And they all share the data that they all share the space that you have on the DRAM, as well as the swap partition on the disk, which is not shown here. Now, the way that operating system manages to guarantee isolation of data from one program from the other is by instantiating one page table per process. So in this case, I have two processes, one for Chrome and one for Word, and they each have their own page table as highlighted by these two different colors. So the golden color is for Chrome, the blue page table is for the Windows Word document. Now, when you look at the mappings, you will see that the virtual address 0 is stored in the physical page 5000. So this is 1, 2, let's say this is 2, 3, 4, 5. So the physical page is actually stored, that is used to store the 0th virtual page of Chrome is 5 the physical page of the main memory. And similarly, the 1000th virtual page of Chrome is stored in 0th physical page in the main memory. Now let's take a look at Word. Its 0th virtual page, and notice that the virtual addresses of two different processes can overlap with each other. And this is to be expected because as far as each program is concerned, they are in their own world as defined by their ISA. So program Chrome has a view of an address space that goes from 0 to 2 to the power 64. Program Word also has the exact same address space. But Word 0, the virtual memory, is stored in a different physical page, 1F000. And so let me say that this happens to be the physical page 1F. So that's where this data would be stored. So let me highlight this using my highlighter. So this data is going to be stored over here. Okay. Now you can see that, let me highlight the 0th data for my Chrome as well. So this is the data, the green data corresponds to the address 0 of Chrome, is stored in a different physical page. So this example illustrates that the virtual address 0 for Chrome is stored in a physical address 5. The virtual address 0 for Word is stored in a different physical page in main memory. And the way that operating system keeps track of all this is by allocating a different page table for individual processes. So when Word asks for virtual address 0, Windows operating system would check the page table and say, oh, the physical page for 0 is actually 1F, and that way it can go and get the correct data. Now the data may not always exist on the main memory. Sometimes it can exist on the disk. So let me highlight this. So in this case, the address 10,000 is not there on the main memory, but the page table says go to the disk to find the data. So if Chrome accesses this address, it would incur a page fault, and that page fault handler would find a victim in this main memory and bring in this page into the main memory. Now when the operating system tries to find a victim for let's say to bring back this red page into the main memory, that victim could be any one of the physical pages. It doesn't have to necessarily come from the same process. In fact, the operating system has a holistic view of all processes that are running on the system, and it knows who's using what and what is being used frequently or which one has not been used recently. And so when it applies the LRU replacement policy, it is applied globally across all the processes and their pages, not between processes, between the pages within a process. And that's an important thing to remember. So the LRU policy is applied globally across the different processes. Now, in addition to isolation, which basically is a property that means different programs don't get to access each other's data, virtual memory also allows you to keep track of some special permissions along with the data. Let's look at a few different types of permissions. Number one, it may allow you to store or keep track of read and write permissions for some data. Now, why is this interesting? So you see this red dot and black dot. I'm going to assume that the red dot is like 1 bit that tells you whether the page is read-only. The black dot tells you that the page is not execute. So read-only means the program can only read from that page, not write to it. Why would this be interesting? Well, let's say the programmer wanted to make sure that the program does not accidentally modify the instructions. So in that case, you want to mark the pages containing the instructions to be read-only. That's not the only situation where read-only pages are useful, but that's a good example. The programmer and the operating system may also want to mark some pages as not execute. For example, you want to mark the data pages as not execute. Why is that? Because it's the instructions that should be executable, but you rarely ever want to go and interpret a data item as an instruction. In fact, in the past, when such protection was not available, it led to this common vulnerability called buffer overflow vulnerability, where an attacker can overflow a data buffer if there is a bug and redirect the execution of the program to that data buffer. And because the attacker gets to define that contents of the data buffer, the attacker can specify whatever instructions he or she wants the program to execute, which is a significant problem, which you can avoid by marking the data pages as not executable, so that even if the programmer makes a mistake and if there is a buffer overflow vulnerability, the attacker won't be able to take advantage of it. So those are the couple of reasons, and if you want to go more deeper into it, I would encourage you to consider taking 482, which is an operating systems course, and also a security course that may give you more details on how to take advantage of that functionality of virtual memory. In addition to keeping track of the permissions, another feature of virtual memory is that I said it allows you to isolate different processes from accessing each other's data. Sometimes you may want to enable sharing between different processes. Now, why would that be interesting? Well, let's say I have two programs which both trust each other, and let's assume that Google and Microsoft, they trust each other, and so the Chrome browser happens to use the same libraries that Microsoft Windows happens to use. And now if both of them share the same library code, there is no reason why you want to have two duplicate copies of that in your physical main memory. You could just have one copy of that shared library, and then your virtual address space can map to that same physical address. So in this case, I have two different virtual addresses from Chrome and from Windows, and they both want to use the same library, let's say, and let's say that library is located in this part of the physical memory. Now I could just store an address in my page table that refers to the same location. Now, in order to enable such sharing, typically a program has to ask the operating system for it. So Chrome has to say, please let me access this shared library and share this with another process. And it has to specify the ID of the other process. So now the operating system knows that Chrome trusts Windows Word. And similarly, Windows Word would say, I trust Chrome by providing its process ID. Now the operating system knows, okay, these guys trust each other. And so therefore, it then allows these two processes to map to the same physical space. So to summarize, virtual memory's main functionality is to provide sufficient capacity for individual processes, but it also has these security features. One that enables isolation between processes, which gets relaxed in some instances, like I just described, for shared libraries between trusted processes. And it also enables special permissions like read-only and not execute which also allows us to improve the reliability of your system. So the last topic I want to touch upon for today is to discuss how virtual memory concepts are integrated with the cache design that we talked about before. So the main question is, what address would you use to access cache? When we talked about caches, we just assumed we'll always use the address generated by the load or a store instruction, and that is a virtual address. So what happens in that case is the pipeline executes a load or a store, it computes the virtual address, and that virtual address is then given to the processor's cache, and the cache figures out whether it is present or not by comparing the tags, etc. Now, if it is a miss, we said we'll go to the main memory and find it when we discuss caches. But now we know that we cannot just access your main memory just with the virtual address. We need to get the physical address, which means you need to do an address translation. In the next class, we'll talk about more deeply about how to do this address translation faster. But for now, assume that you'll go to the page table, find out what the physical address is, and you'll get your physical address. And using this physical address, now you can go to the main memory and access the data for cache misses. So this type of an organization is called the virtual cache. The reason why we call this as a virtual cache is because it is indexed with the virtual address. Now you may have guessed it is also possible to index the cache using physical address. So that organization will look something like this. So the pipeline generates the virtual address. So instead of directly accessing the cache, I'm first going to do the address translation, and then I would get the physical address. The physical address will then be used to index and access the cache. So all the tags that you maintain in the cache and the hit or miss, etc., they will all be defined based on the sequence of physical addresses as opposed to virtual addresses. And of course, if you get a miss, you already have the physical address, so you can go to the main memory and get the data. There are some trade-offs between these two designs. The virtual index cache versus physically indexed cache have different trade-offs in terms of complexity versus performance, and we will get into those details in the next lecture. But for now, the takeaway here is that all the concepts that we talked about in the virtual memory, where there are these two different types of addresses, you can design a cache that operates either with the virtual address or a physical address. And there are some trade-offs involved which we haven't gone into depth yet.